All right. Welcome back, everybody, to the last official class. Can everybody hear me? Yes? Good. So what I want to do today is finish up this some of the security issues we're talking about and push them into distributed systems. And at the very end, I'll talk a little bit about some of the many-core operating system work that's being done here at Berkeley to give you a flavor of some of that research. So a couple of things you might remember from last time. One of the things we talked about was secure hash functions. There were several of them, MD5 being one you probably ran into if you ever download software. SHA-1 is more secure. SHA-256 more secure yet. Basic idea is it turns a big block of data, whatever the size, into a fixed set of bits. Okay, so how could we use this? Well, one of the things I showed you was potentially using an untrusted server to download data from, as long as you can get the hash from a trusted server. So the idea here is we have an insecure mirror, and it stores the bulk of all the files. And we have a secure server, which we set up some connection with based on a public key encryption or something else. And first we ask the server for the hash. And once we've got the hash, then we can actually ask the data mirror for the data. And it can only give us back a file that's correct because if it gives us back an incorrect file, we can catch it because the hash will be different. All right, were there any questions on this piece? Now, if you notice, I had several properties of a secure hash last time, and sort of the summary of those properties was that it's not possible without an extraordinary amount of computation for an adversary to come up with an alternate file Y that has the same hash. And that's what the secure hash part is about. Okay, is everybody clear on that? Okay. So then the other thing we were talking about at the very end was public key encryption, which is kind of magic in the sense that when it first came up, people thought it wasn't possible. And then once it happened, then suddenly you could build all sorts of infrastructures on it. And the basic idea is there's two keys, a public and a private key. Typically, they're symmetric in the sense that you could make either one of them public and the other one private. It doesn't really matter, but one of them typically is made public. The other one's typically made private. And you can't derive one from the other easily. And we showed a typical setup of a secure channel where Bob sends his public key, and as a result, Alice can encrypt things with the public key that only Bob can read. Alice sends her public key, so now Bob can encrypt things that only Alice can read. And if you think of those together, they become a secure channel, and because it gives both privacy from the encryption standpoint and restriction on the destination. Okay, so that's really a secure channel. And in addition, you can sign messages in the way that we talked about here. So this is basically taking some well-defined phrase like I'm Alice and encrypting it with the private key of Alice. And as a result, when Bob opens this up, he can take a look, and only Alice could possibly have sent this message because only she has the private key. And Bob can decrypt this little Alice signature piece with her public key and verify, therefore, that she's the one that sent it. Is everybody clear on that? So this is how you get both a secure private channel and kind of authentication. Okay, were there any questions? Because we're going to use these ideas in a moment here. Okay, and I also talked about general signatures where you have some message M that you really don't need to make private. In fact, you probably want it to be public. And the idea here is you take a hash of M, which the hash of M, remember, is like a unique token that defines M. That's what it means to have a secure hash. Then we encrypt it with X's private key. And as a result, we pass this tuple of the message and the signature into the wild. And somebody can basically check this signature by taking the hash of M and using X's public key to decrypt the hash, compare the two, and if they match, then we know that it must have been X that signed it. Okay? Good. All right, that was kind of where we left things. Are there any questions on that piece? Yes?
For choosing the private key, is it as simple as just choosing a couple random numbers
Typically there is a process involved in making a public-private key pair. And randomness is usually involved, but it's not quite as simple as any random number can serve as a public or private key. There's usually certain properties to both of them. Oftentimes randomness is used to, at the beginning, for instance, in RSA, to select the two prime numbers, and then some additional randomness is used to get the right properties for the public and private key, but it's a little more complicated than just a random number usually. Okay. Any other questions? Sometimes that randomness, by the way, comes from you typing. So that's actually one way. When you generate a key, it says type some digits, and it's the timing differences that are the randomness that they use to help generate the keys. How many of you actually have a public-private key pair that you occasionally use? How many of you sign messages with it? Less of you, yes. Surprisingly, there are actually some pretty public mail readers that are out there that know how to deal with public and private key pairs. It's very easy. You just have to get the right plugins, and then you have to have people you're sending to that are actually going to check and make sure it's really from you. But anyway, okay. So today we're going to actually use some of these cryptographic mechanisms a little bit more. We're going to talk a bit about how you might build a distributed storage system. This is going to be a very quick slice through the typical stuff that peer-to-peer people worried about. And then we'll talk a bit about some worms and viruses that have occurred. And then we'll close out with many core operating systems. And we have to end a little bit early today because they're going to do the reviews. So I will disappear at that point. So if you remember, but I'll be back next Monday. If you remember, we talked about authorization, which was the who can do what matrix. And remember how this matrix kind of had things that you're protecting across the top and things who might have access along the side here. And we talked about kind of two approaches. One was the access control list. And the other was the notion of a capability list. And in this case, capabilities are often sort of in a cryptographic key that gives you access to something. It's a piece of cryptographic data that you could pass around to somebody. And that piece is basically looked into, and then somebody might decide whether to give you authorization. You can imagine, though, on a local single host, it's very easy kind of in principle to do authorization because you look up an identity. It's the databases are all local. Maybe they had a password that they gave you, and this table in some form is local. What gets more interesting is if we have a distributed system where we have to somehow do authorization remotely, then what? Okay? And one of the biggest problems that you run into, and how many accounts do you think you own? Right? How many computer accounts? Can you count them on your hand? Do you have 10 of them? Probably a lot. You got sort of the instructional account, and maybe from several different courses, and then you've got other accounts that you use. You probably have Yahoo accounts, Google accounts, whatever. By the time you add up all your accounts, you've got many passwords, many usernames, and a mess. And so I would say that in order to have a truly distributed authorization, you got to do something better than that. And one question you might ask, for instance, are all usernames in the world unique? Okay, do you think that your username that you have on your Berkeley account is unique? Probably not, right? So, for instance, it is kind of amusing that Kubi, K-U-B-I, at MIT.edu is actually an email address that will get to me. Now, what's interesting about this, and this is from I had this from quite a while ago. And there was a point at which, however, there was somebody else who went by Kubi at MIT, and their friend, thinking they were clever, sent a very private email. I won't go into the details, to Kubi at MIT.edu. I got it. I said, I think maybe you meant somebody else. I'll delete this now. So clearly we have some uniqueness issues. And you need something better to identify a person than a username or an email address even is not as unique as you might think. And so this is where it gets kind of dicey. Like if we want to be able to log into any server anytime, what we just talked about earlier is you have all of these different usernames, and you have to remember them. Okay, that sometimes gets a little tricky. I mean, how many permutations of Kubi, J, Kubiatowicz, Kubatron, yada, 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 do you think I have on different websites? There are a lot, and those are my usernames, right? So it's a challenge even to remember them. And so you need an account on every machine in order to really make things work. And maybe instead of an account in the more traditional sense, what we really want is something more universal. And this is where public-private key pairs come into play. And especially when you've got 1,024 bits or a 2,048-bit key is probably a better thing these days, then it's going to be unique with very high probability. Okay, it's highly unlikely that somebody is going to run the process for generating a key of 2,048 bits and they're going to come up with exactly the same public and private key pair. It just isn't going to happen. And so perhaps we can use these public keys truly as principals to represent you. Okay, and now this almost becomes the universal username. Okay? Is everybody with me on that? So now, how might you use it? And let's construct an authorization scheme that might use public keys to access files remotely. So you've got a client, and there's some server here, server 1, which is in a different domain than the client. So by domain here, I just mean password domain. And this file that I'm interested in, which happens to be stored on server 1, is owned by somebody whose owner key is a public key and is written into the file. And what we'd like to do is we'd like to give access to that file based on what it is that the owner wants. Okay, now the owner is going to build, for instance, an access control list that is based on public keys of entities that they want to have access to the file. Okay, and this is one of many ways to do this. But so what we would do is, first of all, every request, here's readx or whatever, is going to be signed by the client. Okay, and the reason we want to sign it by the client is because that server needs to know the client was the one who made this request. And the only way to know that the client was the one who made the request is because the client signs it with a public key. And I say K sub client is basically the private part of that public key. Okay, and we'll probably pass along what our public key is or what a certificate is binding, showing that that public key is really who we say we are. Okay, along with this request, even though this is technically public knowledge. Okay, and the reason we include this in the message is so that it's easier for the server to figure out who's coming along. Because they get this key, they can check that it's a valid key by checking the certificate, and then they can see that this public key really does potentially sign this thing. Okay, and so they're simultaneously checking that the person who sent this has the private side of this key and that the public key somehow represents somebody we're willing to deal with. Okay, so we can say a lot by signing a message and sending the public key certificate along with it. Now, what might we do with that? Well, suppose we've got an access control list for this file. What's going to be in it? Well, a bunch of public keys is a possibility. So here, this says, well, this key has read access. This key has read-write access. This group key, okay, is for a group of people, and that actually has read and execute privileges. Okay, so now how can we know that this access control list is officially certified by the owner? What would we want to do with it to certify it by the owner? Yes? Okay, now we may not want to encrypt it. Yeah, so we could encrypt it with a private key. What's a little less drastic than encrypting the whole thing? Sign it, right? So we might sign it. You have the right idea there, right? So signing is you basically take the hash, you take a timestamp, you sign it by the owner. And now this access control list is officially certified by the owner as being an OK access control list. Why? Because the owner signed it. Is everybody with me? Questions? Yes. What it means for the owner to sign it is, notice that the owner is not this server. The owner is a person, a principal. And what it means for them to sign it is they produce this access control list, and then they generate the hash, and then they encrypt the hash with their private key, thereby generating this little yellow thing, which I call a verifier, which is essentially the signature. And the reason I have a pointer from the owner key to this verifier is that this owner key verifies the verifier. Okay. Now, what does the server do? Well, the server takes this key and it says, oh, is it in my list? No. Okay. Now, the reason I made this more complicated is just to make it more interesting. Certainly none of the single keys match my private key, or my public key, I mean. But here's a group key. So what does that mean? Well, that may mean that I need to read the group. Okay, and what's the group? Well, the group is maybe on a different server, there's an access control list signed, again, by the group key. Okay, so the group key signs this subgroup. Okay, and then the owner signed this access control list. So notice that we have a chain of custody, so to speak, from the original owner signed this access control list, a key in this access control list signed this access control list, and by the time we get down here, notice that these two keys match, and we might say, voila, this thing actually, this original reader actually has proper access because we're granting read access to the group. Now, why am I giving you a complicated example like this? I want to show you that you can build an interesting arbitrary tree of signed documents using public keys, and now their authenticity is kind of based on sort of each link in here. And ultimately, it's the owner who signed the first one that signed the second one that basically authorizes kind of by proxy this access. Question, yes?
So who signed the group access?
Good question. So who signed the group key, group access? Give me, speculate.
Probably not the owner.
Must be some, so what do we have to have here in order to sign in the first place? We need a public-private key pair, right? And here's the public half of it. So the signer has to be somebody who possesses the private key. That's the other half of that. And so now what I'm saying here is the group is like an entity in itself. So there might be some person who has the ability to add and remove things from the group. They're the ones that have the private key. Yes?
So would like multiple people in the group all have the same private key or something?
Well, only the people who are authorized to change the group. But notice that you could actually, this person here is kind of in this group, and he doesn't necessarily have the private key here. Only the person who is authorized to add and subtract from the group has the right private key.
Well, like in that example, there's like two keys. So is it like two different people have like their keys stored in the group?
Yes, so there's two different people that are in this group. But neither of these people may have the ability to add or subtract people from the group. So think of a system administrator might be the person that actually has the private key associated with this. And these are regular users who happen to be in this group. Okay? Yes?
We're doing a lot of public-private crypto for every file access. Is there a way that you can optimize this?
So you could, so as you are kind of implying, which is true, public-private key cryptography is expensive, and symmetric is much cheaper. And so there are schemes that basically try to make sure that you don't do too many of these operations. Well, so in this particular scheme, you're still going to probably have to do public-private for every hop. But in terms of encrypting the file, what's probably going to happen is you're going to encrypt a symmetric key with the public portion of this and then use that to encrypt the rest of the file. So for things that are bulk data, typically you try to use the symmetric encryption to make it faster. But often, anything where there's a link like this, it's going to be probably a public-private key pair. It's very hard to optimize that case.
No matter what your file access is.
The initial file access, although potentially once you've been granted access, you could imagine some sort of cached access control thing. Good. So by the way, what comes back from this server is, yeah, you had access, and then that generates the data, which goes back to the client, and it's signed by the server, let's say. Okay? Now, is this the right scheme? Well, this is a scheme. Okay? I just wanted to give you this to illustrate what you could do. Among other things, the access control list can be widely spread. You could have an access control list in China and one in Europe, and the client could be in the US. And the thing is that this process of verifying is still good. Okay. Questions? Now, this kind of tree of signatures, by the way, is exactly what a certification authority does. Remember how we talked about them last time? What they do is the certification authority, like VeriSign, is the one with the owner key. They sign your key, where your key now is in the replacement of the access control list. In fact, what often happens is VeriSign signs an intermediate key like a Berkeley key, and then Berkeley is allowed to sign keys off of the Berkeley key. So, for instance, our IT department here has a special key that allows them to sign other keys. And so when you get a certificate out of the IT department here, you'd actually get something that might be kind of a second-level key. So it's certified. The VeriSign certifies the top-level key, which then certifies the second-level key. So you can build these kind of trees all over the place. Okay. Now, what about this previous scheme? So the positive points here is identities are checked via signatures and public keys. So client's not allowed to generate a request for data unless they have the private key to go with the public identity. Server won't use access control lists that are not properly signed by the owner of the file or by proxies to the owner like the group key. So this is all good. Multiple domains don't really matter because we're not actually using real accounts. We're using public keys in all of this. So that's good. What about revocation? Suppose that private key gets out. Now you got problems. Okay, so somebody steals your private key. Now suddenly your public-private key pair is no good. Why? Because the private key is out. And what do you have to do? Well, you have to walk through this whole tree of access controls to hunt down every place where your key is. And then you got to get things re-signed with a new key. Right? Imagine, millions of files that it may have to trace down, or zillions of files, where zillion is big. What do you do? This is a mess. So revocation in a scheme like this is not very good. So what can you do? Other than cry. I heard that. Yes?
Another layer of encryption.
Okay, how would you do another layer of encryption? I suppose you could try to, you could put a password on your keys. That's true.
And then they would force them. They have to brute force them, giving enough time to replace them if necessary.
Maybe. So you're basically trying to make this more complicated to deal with, so that you have to work your way. You can have more time to fix it. Yeah. Okay. But what else can we do without having to go all the way through? Go ahead.
Augment the top-level access control list with a revocation list or a banned list, and just have the owner.
Yeah, so that was a good solution, by the way. But this one also works. So what I think you're saying is, what if instead of the owner being defined by their key, they're defined by something else, like a token name, something else that's random? Maybe you weren't saying that. So here's another thought, is you have a unique string identifying you. And here truly a random number could do fine. And in this case, what you do is you get a certification authority to sign the fact that the random number and your public key are associated together and represent your identity. And then you put that random number in all the access control lists. Okay, and now if your public key is, or if your private key has been compromised, all you need to do is get a new public-private pair and a new signature signing your randomness with your public key, and make sure that you have revocation notes out all there saying, well, that old one isn't valid anymore, and you don't have to touch the access control list. Because what you're doing in my second scheme here is, now what you're doing is, instead of this just being a key, it's actually a certificate that says key random string identifying you, signature from VeriSign, and it's that random number that's in here. So you're not actually hunting down and changing the keys in here. You're changing the random number. Yes?
So last time I think you were saying something about how the way they do it is good because you don't have to like access a server every time you want to like check. Like yeah, like it's like better than Kerberos, like this new scheme.
Right.
But then if you do this, do you have to go and check with the server that the token matches the
Well, what the servers, so the server in Kerberos' case was you had to actually have the main server up, whereas all that has to be up in this case is the set of servers that are serving your data, which is a little bit less of a problem because if the main server goes down, well, there isn't a main server. It's sort of everybody whose servers are still up can go. Yes, question in the back. So this is where VeriSign or somebody comes into play. Because they've got the data that says that token and the public key are associated and they've signed it. But that's an offline store. It doesn't actually have to be online because it's. So the way the main server now, these are all great questions. So what about revocation? Well, what you do is you try to make sure that the revocation lists just get out to every server that could care. They don't have to be online necessarily. Yes? What does the certification authority do to protect itself? That is a really good question. Not always successful. I think the biggest thing about a certification authority is since they don't have to be online in the sense of serving requests, you can make them mostly offline, and they're harder to break into as a result. They don't actually have to be sort of actively on the net. Yes? So, okay, so hold that question for a second because I haven't gotten there. So all we've been talking about is access control. We haven't actually talked about, A, how to make sure the file isn't exposed, and B, how to make sure what happens if this server has been compromised, then what? So we haven't actually, that's a good question. Hold on to it. So again, this is not the ideal, the best scheme, but I'm giving you some options. You can see how with public-private key pairs as a building block, you can build interesting things. Okay, very interesting things. And that's kind of why they're so magical. Okay, it's like an offline server can be set up, which is a certificate that's floating around as data. You don't actually have to have a real server up. You have to have the data. And so that changes it from I have to be able to talk to a physical piece of hardware to I have to be able to find a physical piece of data, which is a certificate. It's different, right? Because then I can replicate the certificate. I can use peer-to-peer techniques, which I think I'll talk a bit about on Monday, to replicate them anywhere and find them. I don't actually have to have a particular piece of hardware, just a particular piece of data. It's a very different viewpoint. There was a question in the back? No. Okay. What if you remove somebody from an access control list? Well, ideally, that change would get propagated to anybody who could read the access control list. Here is a case, actually, where inconsistency in caching, because you have old copies of things, and security are directly kind of in opposition to each other. Okay? Right? Because if you have old versions of this, so again, let's look at this. This access control list is on some server somewhere else. I removed person X from here because they're no longer in my group. And however, this particular server has an old copy of the group ACL, okay, because it hasn't been invalidated yet. Well, it might tell me the wrong decision, right? So cache consistency in the sense of making sure that changes are propagated immediately and security are kind of hand in hand in this situation. Yes?
So, I just have a question about the random value pair with the private key.
Sure.
So if someone steals your random value, you still have the same problem as before if someone stole your private key, right?
No. And the reason not is the random value is in some sense public information. It's a string of bits that is uniquely you. What happens what does VeriSign give you when you go to VeriSign? It actually gives you a certificate that's both your public key and the information identifying who you are and what you are, you know, and what organization you belong to and all that stuff. And that's what's signed. All of that's public information. so it isn't like breaching the random number matters. The only time where breaching that random number would matter is if you're trying to hide whether you, as person X, are in a given access control list. That might be a reason to hide it. But from a security of the access control list standpoint, that's not a problem.
So if someone steals your private key, then they have your private key and your random number. So how does this stop you from having to change all the access control list?
What it changes, so that's, let's go over that again. So what's in here is the random number, which identifies you. It's the certificate associating your public key and the random number that's been signed by somebody. Let's suppose the private key is breached. Now you need a new public-private key pair, and you keep the old random number. You associate public key, random number together and sign it. And however, there's these old certificates floating around. And that's where you need to make sure that there are what are called revocation certificates out there from VeriSign that says, well, this old public key is no longer good. And so they need to be propagated to the world. Okay? But you get a new certificate associating your new key with your old random string. And so the random string is kind of mostly constant in this scheme I've given you here. And again, it doesn't have to, random could be your name or something if it's truly unique, but random is just easier to be unique. Okay, good. Any other questions? Think of this as building blocks. Yeah, go ahead. How do you know when someone's stolen your private key? Well, that's a problem to know. If they're bragging about how many private keys they've stolen, they may do something that you find out immediately, like steal money from your credit card. On the other hand, they could cache it for years and pick the perfect moment to go after you, and then you don't really know. So, So I'm going to sidestep the how do you know a breach has occurred question. That's a very hard one, not always solvable. So let's go finish up with the data before we go on to something a little different. So who signs the data? Or how does the client know they're getting valid data? All they've done is they've asked the server for some data, and the server's decided to give it back to them. And if it's signed by the server, then we have to know that the server is not compromised. So I ask some random server, it gives me back some signed data. How do I know that that server doesn't have a virus on it and it's giving me back bogus data? How do I know? Okay, I don't. So if we're really paranoid, which is not a bad thing in today's internet, then perhaps we have all data signed by the owner of the file. Okay, now it's not that we're trusting the server, but rather we're trusting the owner to have been careful about their private keys and not given that out. Everybody with me? So notice here, the point at which the data comes back, perhaps we're signing this not with the server, but with the owner's private key. And so now we know that this data is truly correct because the data that came back is signed, and we're trusting the owner rather than the server. Okay? The problem with that, of course, is that now only the owner of the file can actually update it because they're the only ones with their private key. So now when you get more interesting, you can say, well, suppose we don't trust a single server, but we trust groups of servers. When did I tell you about that idea? A couple of lectures ago, right? Remember Byzantine agreement, where a set of folks together make a decision? Okay, well then maybe we trust the group of servers, and in that case what happens is we ask the group of servers to sign things. Okay, and there's something called a threshold signature, which you'll learn about, I'm sure, if you take 161, where each server generates a piece of the signature, and there's a way to put them together to get the full signature. And you can do that in a way that as long as the right threshold number of them are doing the right thing, you can get a real signature on the data. And so you can actually get signatures by proxy, where now this group of servers is acting in proxy for the owner. And what's kind of cool about that is that now we can actually submit updates to the file, and the group of servers are going to do the updates and decide whether they're good and sign things for us. Okay, and that's kind of where some of the peer-to-peer work where we don't trust individual servers came into play. So the final question we might ask is, how do we know the data is up to date? The problem is that a valid signature only means that the data was correct one point in time. Okay? So this is basically a freshness attack where a malicious server keeps returning old data instead of recent data. And a good example here, you just got a raise, somebody updated the database, but a malicious server is returning the old data, and so you get your old wage. Okay? And this is a very hard problem. And this is about invalidating old cache copies, and again, this can be fixed by Byzantine agreement. Okay? Questions? All right, so I'm going to do the administrivia, and then I'm going to show you very briefly how OceanStore used these ideas. I'm going to jump forward here a couple of slides, and then I'll jump back. So, as you know, we have an exam coming up. But before then, we actually have our optional lecture. And I haven't quite decided what I'm talking about, but it will be good. It will be a great time. You guys will love it, I hope. And that's Monday, normal time, normal place. And it's totally optional. Things that I talk about on Monday, you do not have to be responsible for on the exam, unless it's something I talked about earlier in the exam, earlier in the term. Final exam is on the 16th. I know that there was one person that had an actual exam conflict. If there's, there may have been somebody else. Make sure you send me that mail so that I know. Technically speaking, it's all material from the course, although there'll be a focus on the second half of the course a little bit. You get 2 pieces of notes, 2 sheets, both sides, and bring a dumb calculator. Okay? You've all been warned to bring a dumb calculator, not a good one. And it's likely that there will be annoying computation on the exam where you need decimal points and stuff. And so I would suggest you actually having a calculator. Should be working on Project 4. It's due next Tuesday. It's hard to believe that this is the last actual official day of class, isn't it? I will actually continue to have office hours next week if you want to stop by to ask questions about exams or life or whatever. Feel free. And get any regrade requests for Project 1 through 3 in by this Friday if you haven't done it already. Oh, wait, we haven't handed back Project 3 yet, have we? Oh, so, okay, back up. Project 3 is coming in the email tonight to the TAs at least, so we will have them. Last night? Okay. So actually, when I say next Friday, I'll mean a week from 2 days from now. So make sure to get your regrade requests in. Okay, and as far as Project 4, we'll take the regrade requests up until the final because I'm not entirely sure when those will be done. Yes?
So, but you might not get Project 4 until like 6 as well.
Yeah, so Project 4 may not come out until relatively late, so be watching your email. Sorry about that, but you don't turn it in until next Tuesday, and then the grader is going to go crazy, but and he'll try to get it in as soon as possible. I talked to him today. He was saying something like 13th or 14th was more likely, but you will definitely get your Project 3 grades soon, before Friday even, possibly. Okay, any administrivia questions? No. Okay, so now I'm going to very briefly, because I do want to talk about a couple other things, talk about how OceanStore used these ideas. OceanStore was a relatively popular large storage project that I was responsible for back in the early 2000s. And I probably will actually talk about it peer-to-peer land on Monday a little bit more. But the basic idea here was that data was spread very widely all over the world as a way of making sure that it was unlikely to get lost. Okay? And the question was, could you build kind of a cyberspace level storage system that could store data for thousands of years and so on if you made use of all the servers in the world? And I was basically using the pyramids, which I've mentioned before, as kind of my idea that there'd be something that was really stable enough to be around for 1,000 years. Okay, now I will actually, on Monday, I'll talk a little bit about the interesting peer-to-peer technology to make things stable, but I wanted to show you some of the security ideas. And to deal with those, we just need what we've talked about so far. And first of all, we use this notion of versioned objects. Okay, so what's a versioned object? A versioned object is one for which every write generates a brand new copy of the object. Okay, or a brand new object. Now, that does not necessarily mean a complete copy. So if you have a gigabyte file and you write a byte, it doesn't mean there's a whole new gigabyte. What it means is that the changes are registered and you can get something that looks like a completely new file. Okay, and so we can actually talk about changes to files as a sequence of new files. Okay? Yeah, you could say maybe this is sort of the difference between SVN and CVS, although both of them you can go back in time pretty much so.
But CVS is sort of a copy each time, as just sort of changes.
Yeah, I suppose. But, this notion that every update generates a new version is not so much a statement about how it's stored, whether it's stored in diffs or copies, as it is a statement about every version can be treated as a read-only thing that you can replicate widely. Okay, so it's really about the read-onliness here that's interesting. And every version's read-only, so once you create a new version, you can't change it anymore. Okay, and what's cool about that is you can take a version and name it by its hash. So now each version has a unique hash that represents that version. And so you can say, what does a file look like? A file is a sequence of hashes, described by a sequence of hashes. Okay? And therefore, the object, which is the type of file you're used to, is really a signed mapping between the name you're used to, like etc password, and the latest version. So it's really, there's a certificate that maps the permanent name and the latest version. Okay, and I like to think of this as the comet idea. So you got updates to the head of the file, which is the actual file itself, and what's coming out in the back are versions, which are sort of the cometary tail. Okay? Now, this basically, the notion here is that every update generates a brand new version and that you never erase things. That could be one way you go with this. And this was kind of predicated on the notion that data storage keeps increasing arbitrarily, which it does. I mean, we're basically going to have 2.5 and 5 terabyte drives out not too long from now. So I won't go into this, but the way you build a system where every write generates a brand new version is you build a tree. So a file consists of blocks, is really a tree. Does this tree look familiar? This looks like an inode structure, right? But if I build a set of pointers, and at every link here, this is really established by a hash. So what I put in for a link is I put a hash of this block. And then I take the total block and I put a hash of it in there. And then I take a hash of the total thing, and that hash at the top level is the name of the file that's unique. Question? No. So, and now, if I have a new version, all I have to do is build a tree where I only put new blocks in for the changes. So here's a situation where this new version updated block 8 and 9, but the rest of the blocks are the same as the old ones. And I can do that if I have this notion of the world as a permanent storage system where all of this data is read-only forever. Okay? So now a file is really just a set, its top level is a hash. And all I have to do is I just have to be able to hunt things down based on hashes. Questions? So the world is a storage of read-only blocks, and every file is a unique hash. And that hash, in the case of this, gives me my top-level block, which then gives me hashes inside, give me the other blocks, which give me other blocks and other blocks. So just by knowing the hash of the top level, I've got the hashes of every other block, and therefore I can reconstruct the complete version. Okay? It's a different point of view from the way you normally think about it. Question? Yes?
Is this kind of similar to how Git works?
How Git? Yes, a little bit. This idea is pretty. I mean, it's very similar to the copy on write notions that we did in virtual memory systems. I mean, these ideas have been around for a long time, but this is sort of, it's kind of taking this copy on write idea to another level where sort of every block has a permanent place in the world's memory. Okay. Now, and notice that now, basically somebody, which is a central server, central set of Byzantine servers need to be able to send out these heartbeats, which are signs, statements between what the last version is and the permanent name. And I don't want to go into this any further, but here is a version of the OceanStore update slide, which I used to show. Here's Europe. Here's a bunch of clients, which are somewhat older now, as you can see. And the idea was potentially there were all of these read-only caches spread throughout the world. Why can they be read-only caches? Because a hash uniquely identifies the thing I'm looking for, so these can't be malicious. The worst they could do is give me bad data back, but then I can ignore them. And so I can easily put caches of data everywhere. And then we'll have a few of servers that are in Byzantine agreement rings. And the idea is that updates go to those set of servers, which execute a Byzantine protocol and decide sort of which commits to make. And then they sign the result and propagate it to everybody. And so you could basically have something that you essentially were broadcasting to everybody like a video, and you could get really good performance out of it because caching works really well. Everything's read-only. Okay? And sort of here are some of the pieces. Okay, question? Yes?
Does every one of those purple nodes could have like a complete copy of all the data?
Every purple node could have a complete copy of the data, or maybe they only have a copy of the data that's currently being used by people in the local region. Or maybe they have part of a file. Remember, every one of the blocks potentially can be cached independently somewhere. Okay, questions? So this is basically taking what I showed you, this notion of building trees of hashes and signatures to a very extreme extent. Okay, question?
Did you do something in terms of, so do you have some guarantee that even if a collision, if it were to happen with the hashes, could be very dramatic? Do you have some guarantee as to make sure that between two versions you...
So what you can do is you can look it up and see if you're going to get it back. But we were using 160-bit SHA-1, and so the probability of a hash is so low. But probability of collision.
Time that happened, it happened to be the bank accounts.
Yeah, it's true. So what you'd really do is you'd have to check something before you stored it. And then you go to SHA-256, and then the probability is much, 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 much lower. So. Good. All right. So, got this. So let's change gears. Actually, let's take a really brief break because we're running on a tight schedule, and we'll come back and talk about a couple other things. So we have a couple of options here for where to go with the rest of the lecture since we have such a short time. We have one, we can talk about some interesting viruses and Trojan horses type things that have occurred over time, or we can talk about parallel OSs. How many people want to talk about the viruses? And how many want to talk about parallel OSs? Oh, more people. Okay. Why don't I talk about a couple of things here, and then I'll talk about the parallel OSs. And if I don't complete it, we'll talk about them on Monday. How's that sound? Okay. So what about software loaded without your consent? So these are things, macros and so on attached to Microsoft Word, etc. ActiveX controls for a long time were a problem. Spyware included as normal parts of normal projects were actually problems. And unfortunately, you can click on something on the web and it will install stuff on you, and you won't have the ability to know that happened until it's too late, right? And this is a problem. Now, a particularly bad one, which I'd like to mention, is the Sony spyware issue. How many people heard of this? Okay. So this was a very interesting thing. So they had something called XCP, which was the extended copy program, and it was copy protection, and it was supposed to be, I guess they thought it was a good thing, but there were about 50 CD titles back in 2005 that when you put them into a computer, they automatically installed software without you knowing, okay, and that software was a rootkit that basically modified the operating system in a way that would prevent more than 3 copies from ever being made of that CD. And worse, it was reporting private information to Sony, which was annoying a lot of people, and it automatically changed the file system so that generic files of the form $sys_xxx were actually hidden, so you couldn't even know they were there. And a bunch of virus writers figured this out and started exploiting it. Okay, so you put in a CD and suddenly your machine is a vector for all sorts of stuff. And initially it was extremely hard to remove, because if you tried to remove it, it made your operating system unstable and you actually had to reinstall the operating system. So this is the ultimate example, I think, of involuntary installation. It's pretty bad. And right away, a bunch of vendors of virus protection software declared this spyware. And Sony, for months, said, no, it's not spyware. This is our right. This is, copy protection, was basically what they were saying. And they eventually were forced to back down, but it took kind of a grassroots uprising about this. The enforcement part we didn't really talk much about. Remember, we talked mostly about authorization and access control, but enforcement, and saying who you are here, enforcement is this process of actually checking passwords and access control lists, et cetera, to make sure things work. And this is the layer below the access control list. And so if there's a bug in your enforcer, then that's a great place for malicious software to take over. And in Unix, unfortunately, a super user can do anything, but basically you require super user privileges for almost everything that you might need to do at the system level, okay? And if there's a bug in any one of the programs you're running at super user, you've got a problem. So this is really the fact that the access control in Unix is too coarse-grained, okay? And that's a problem. So there's a bit of a paradox here. You can build a bulletproof enforcer, which never has any bugs, and the only way to do that is to make it very small. It's very easy to make correct, maybe if it's really small, but it's got a simple-minded protection model, okay, which is hard to adapt to different situations. Or you have fancy protection schemes, and your enforcer gets complicated, and it's really flexible, but you've got a lot of bugs. Okay, so it's hard to win here. And you could say this is kind of the same argument for Java or C++ about what you make things to be public and private. I don't know if you actually worry about that, but you should. That would be good coding practice. So the state of the world in security, authentication's done with encryption, okay, but almost nobody encrypts or has public key identity. Many of you do, that's good. The state of authorization is some sort of access control, but many systems give you only coarse-grained access control, which is exactly why you have to use superuser as in Unix so much. Enforcement is done by putting everything in kernel mode and assuming that that's correct, except that it's very hard to take your million-line kernel program and make sure there's no bugs in it. Okay, so if you wonder why we've got viruses, it's basically because, because of this. So some types of security problems you've probably run into. One is abuse of privilege, where the super user is evil and then you're basically in trouble. Or a system operator is, went crazy and deleted project 4 before you're able to submit. Okay. Or an imposter. Okay, they get a hold of some some information and they're able to basically masquerade as you. Okay, these are all problems. Okay, now I wanted to name a few things you're used to. So viruses, of course, are a piece of code that attaches itself to another program or file, but typically requires a vector, namely you, to wake it up and do something. You have to actually click on it. The alternative to a virus is what? Worm. So worms are much more insidious because they can break into your machine without you actually clicking on anything. And a lot of the more interesting things out there have been worms in the past, okay? Similar to a virus, but it can travel on its own. It basically takes advantage of bugs in the file system or the network or something, and it can replicate itself, and your computer might send out hundreds of thousands of copies of itself without ever knowing. Okay, and then finally, a Trojan horse is basically, of course, named after the huge wooden horse in Greek mythology. But it's something that at first glance looks like it's regular useful software, but it's really waiting to gather your passwords. Okay, and this is a typical problem with login programs. Okay, so what I wanted to do for one security problem here is buffer overflow. So this is a very interesting security problem. Here's a piece of C code where you have a buffer that has some size, 256, and you do something like this. String copy from argv1 to the buffer. So what's the bug with this code? What happens if this argument is 258 bytes long? Yes? Yeah, it might not be null terminated. That would really be a bug, or it might just be too long. Either case, you end up overflowing the buffer. And here is a stack frame with the return address. Remember this from the beginning of the class? And maybe the frame pointer, and here's the actual buffer, and so on. And the problem is that because this code doesn't check for the length, if you write into the buffer, it's easy to possibly overwrite not only the buffer, but also things like the return address. Okay, so now what happens when this procedure returns? Well, instead of returning to where it originally came from, it returns into this code that was downloaded and starts executing it. Okay, this is called a buffer overrun bug, and this is a very common problem. Okay, many network attacks. Anytime the input comes from a network request and is not checked for size, you got to be careful. Allows execution of code with privileges as the same privileges as the running program, which in many cases might be root. How do you prevent this? Okay, one possibility is never code like this. Okay? Or, as was set up here, sanitize your inputs, which basically makes sure that you never actually have an input that could do this. What else?
You just enforce, like if the buffer, or force controls on the size of the buffer.
So you could force compilation of this with a compiler that knows automatically checks for buffer overrun. Okay, the problem is that in neither of these cases are really plausible. And what's more interesting is newer bits in the PTEs, basically from Intel, AMD, and Sun, allow you to set pages as being non-executable. And so what that really says is you take the stack page gets marked as non-executable, and then even if they manage to do this and download this, you won't actually be able to start executing the code that's been downloaded. Doesn't address the issue with overwriting and screwing up the code, but it makes it much harder to execute arbitrary code. So Okay, and I always want to make sure that you hear about the Morris worm. How many people know about the original Morris worm? A few of you? Okay, so the most interesting, so Morris was a first-year Cornell grad student. He thought he was doing something very cool. And what he wanted to do was basically create a worm that would go to every machine and basically say, hi, I'm here, look, aren't I cool? Okay, and it was launched at the close of workday, November 2nd, 1988. And within a few hours of its release, it consumed resources to a significant fraction of the internet. Okay? And what it did was, it actually did a combination of remote access, where passwords were lying around in certain cases, bugs in the finger program, which we don't really use much anymore, but that was a buffer overflow. The sendmail programs that were commonly distributed with BSD Unix had a debug flag naturally in them, and that debug flag lets you log into the sendmail daemon on that machine and execute arbitrary code. Okay? They also, once managing to get into a particular machine, first it would download a piece of code called the grappling hook, which would reach across the network and pull the rest of the worm in. One of the things it did was it ran a dictionary attack against the local password file, found all the passwords and usernames, and then used those to attack other machines on the network. Okay, because if you use a given username and password on one machine, maybe that works on another one. Okay? So this was a disaster. I mean, this surprisingly pulled down a significant fraction of the internet at the time. And the amusing thing about this, of course, is that Morris is now a faculty member at MIT, but he actually has a felony conviction, which makes it hard for him to travel. So this is not something to be recommended. Let's see. I think I'm going to pass on these two guys. I want to tell you about a timing bug, which is kind of fun. So this was a system in the early 70s by BBN. And it was one of the most popular systems before Unix. And it was thought to be extremely secure. And it was thought to be extremely secure because the code was made public, and everybody looked at the code, and nobody found any bugs, and so that seemed great. However, one release, within 48 hours, somebody figured out how to get every password in the system. And this was not by using a dictionary attack. What it was something very simple. Here's the typical password check code that gets called by other code. Okay? It says for I equals 0 to 8, go through and see if the user password passed in is equal to the real password. Or is not equal, go to error, and if you make it all the way through, you get in, your password's checked, and you're good to go. So there are 256 to the 8 possible password combinations, right? Okay. Wrong. Here's why. All right? So it used virtual memory, even for the part of the code that was checking passwords, and it interacts very badly with the above code. So the key idea is you force a page fault to tell you something. And so what you do is the string that you pass in for your password, you arrange so that the first character of that string is at the end of a page and the remaining characters are on the next page. And then by reading a whole bunch of pages, you basically kick out all the pages, and then you read this page that has the first character. So now we've got the page with the first characters in memory, the rest of the characters are not in memory. And you pass it off to the password program. Okay, what happens? Well, if the password you passed is wrong, you come back really quickly. Okay, if the first character is wrong. And if the first character is correct, you go on to the second character, cause a page fault, and it takes much longer to come back. Okay, so basically, by putting the password like this, you're able to figure out with only 256 checks at max what the first character is. And then you put the first 2 characters and the first 3 characters and so on. And you end up with only requiring 256 times 8 checks maximum to find the password. So this is a case where timing matters. Okay, now you may say, well, this is obviously a clear lesson and nobody would ever do anything stupid like this again. But it turns out that crypto cards, which I've mentioned to you guys a couple of times, which in theory hold keys and do cryptographic operations, there have been timing attacks that have been put against those cards that have been used to be able to extract what public keys they're holding or what private keys they're holding. Okay, and again, it's the same kind of idea. You look for something where the timing differs based on a match or not a match or based on how the algorithm works, and you can figure out what the result is. Okay. So tomorrow, on Monday, we'll actually talk about many-core, because I want to spend enough time to do that. Do we have the person who's going to give the... yes, good. So what we'll talk about next on Monday, if you guys come, is I will talk a little bit about tessellation, which is the new operating system that we're doing here at Berkeley. And basically, the reason for it is that, or the reason for the PAR lab, as I mentioned at the beginning of the lecture, is that we really have many-core chips now. And the question is really, how does this change our view of OSs? And what you'll see is here that many-core is basically a challenge, because we need to somehow take advantage of parallelism and use all those processors. And potentially, it allows us to actually change the way we design operating systems. And so I'm going to make an argument and a pitch for that on Monday about how many-core actually is a potential call to arms to go and reevaluate all of our operating system mechanisms we've been talking about all term and say, can we redesign them now that we've got all these processors? All right, so let's, in conclusion, we'll talk about that. So in conclusion, we talked about using cryptography for distributed identity. We talked about a distributed storage example where things got interesting. How do we revoke? What do we deal with integrity of the data? What about freshness? We talked about buffer overrun attacks. And next time, we'll actually talk about space-time partitioning. That'll be very interesting, sort of how does the rubber hit the road with many-core. So I'm going to say goodbye now. Optional lecture will be on Monday. It will be in this room. I want to thank the TAs. They've, I think, done a very good job. Let's give them a hand. All right. And I will say goodbye until Monday, where I will give you an optional lecture, which will have nothing to do with this course. All right.